Okay. Well, thank you very much for the invitation. It's very nice to be once again here, to see you, everybody, in person. I'm going to talk about several works we have been developing during the last 7 years. These 3 ones and two incoming ones. And in these works, there's collaboration with Marcelo Leves, Cesalio Dominguez, Alejandro Ayala also works in one of them, Luis Hernandez, and Renato Zamora. Okay, so this talk, I'm going to make an introduction to finite energy sum rules. Yeah. The formalism, and explore some 2 channels that will be the axial channel and the nucleon channel. That will be the channels we will explore them at a finite magnetic field. And, well, define the propagators will be used. What happened with condensates in general because of the effect of an external magnetic field. All the condensates in the operator product expansion will be split in more condensates. And once again, the axial channel and the nucleon channel at finite magnetic field. And the nucleon axial coupling constant, that's last work, not yet published, but well, what's the results we have. So, of course, there are a lot of sum rules in the market. I'm not going to talk about which is better, which is the best, or every sum rule has its advantages depending on the problem. I just will talk about the finite energy sum rules. And we start with 2 current correlator. Here, for example, vector correlator. And after Fourier transformation, this correlator has this form, a longitudinal part and a transverse part. Okay, and the spectral function, you can write it as the imaginary part of this correlator. So this is a graphic of a plot of a spectral function, and usually you have a sharp resonance for stable, almost stable particles, and then there's the higher resonances, and then there's an overlap of higher resonances. So there's a point where the resonances start to overlap, and this is a phenomenological energy parameter that is known as the hadronic continuum threshold. So usually people use the most popular sum rule is the Borel transformation of both sides, the hadronic sector and the QCD sector. And it commonly uses the narrow resonance approximation that just pick the lowest resonance, and the rest is just the overlap of resonances that is described by pure QCD. In this case, the hadronic threshold usually is fixed, depending on how many resonance we left over, and they use an extra parameter, than mass parameter, that has to be fixed when the results are stable. In this case, in the finite energy sum rules, the hadronic threshold is not fixed. It's a result of, it's one of the parameters we have to find out, which is. So, how do we match the hadronic sector with the QCD sector? basically this is the Pac-Man contour. And we said that the hadronic degrees of freedom lives over here, and the quarks on this circle, okay, of radius. The radius is 0, the hadronic threshold. So to ensure that the QCD never touches the real positive axis. So using the Cauchy's theorem, you integrate over this path, with the correlator multiplied by some analytic kernel. So the thing is, we separate then the hadronic sector over here and the QCD sector on the circle. And possible poles that could appear, that indeed appear at, if we are considering medium effects, there will be some poles. Those are from the QCD sector. And then we use operator product expansion. So there's this is not equal, it's plus, okay. So we separate the perturbative QCD plus the operator product expansion. And those operators, time order operators, are the condensates. And here is the Wilson coefficients. Yeah? So we are, in this case, I'm showing in the case where we're considering energies higher than the current quark mass. These are normal ordered condensates. So mu is a ms bar subtraction scale. So everything here is well defined, except that there's a problem when you try to get the chiral limit when you have two flavors, and you there's an inconsistency in the sense that if you set first up quark to 0 or down quark to 0, or both the same going to 0, give different results. And this inconsistency goes out when you consider the non-normal ordered condensate. That, for example, here the quark condensate is the non-normal condensate, plus this is the propagator, the full propagator, including the gluons. So this fixes this inconsistency, and then you have, for example, the perturbative part. It's usually a log of minus s. When you go to the chiral limit, it's give different results if you go with the up mass going to 0 before the down mass, or if you set both equal, they go to if you go to 0, then give different results. And okay, the operator 2 is 0. Operator 4 dimension is the gluon condensate, and the quark condensate multiplied by the quark mass. Operator 6, the mixed condensate, 3 gluons condensates, QQ bar up to square, and the mixed condensate, and so on. So the phasors, one of the advantages of the phasors is that they cut the OP series. This is an infinite series, but if you use this analytical kernel, it cuts exactly the series. You don't need to suppose that approximate in some stable in some region that everything turns stable. For example, like Borel sum rules. Also, the hadronic threshold has an order parameter. At finite temperature, the hadronic thresholds turn to diminish up to well, with the shape as similar to the Polyakov loop. And well, also there is not needed to calculate the full form factor because we can integrate first the contour. So that's a technical fact, but it really simplifies calculations. Okay, for example, this is an axial correlator. For one side, you have a QCD that usually we calculate here the channel which includes the charged pions. So it's axial. The pions enters here like as an axial current. And also, if you want to get better results, we include the A1 method and so on. So here's the axial correlator. So this is a transverse part and a diagonal part, parameterized in this way. The pi 5 is the derivative of the correlate with the one derivative of the axial current, and psi 5 is the correlator of the derivatives. And there is a word identity, so there are two of them that are related with this word identity. So from the hadronic sector, for example, we can consider just pions, and then the perturbative part, the typical quark condensate diagrams. Gluon condensate, which is proportional to S squared, and also the quark condensate. So if we consider up to operator of dimension 4, we have this set of 4 phasors, and they are exact equations in the sense that the phasor cuts all the other contributions in the operator product expansion. So considering just pions only, we get this hadronic threshold. If we include, well, I didn't put all the results, but for example, the current quark mass is about 10 MeV, and if we include the A1 resonance, the hadronic threshold is about 1.2 GeV squared, and the quark masses is about 5 MeV. That's more known. If we include radiative corrections, the results are much better. Okay, this is the other example that we're going to explore. Nucleon correlator. So to work with it, we use the nuclear interpolating function. This is the Joffe interpolating function that includes the quarks distribution in the nucleon. It is in the QCD sector. For example, this is a proton. And in the nucleon field in the hadronic sector is just the nucleon field times a constant that is known as the current, nucleon coupling current. So at vacuum, the correlator can be separated in one part is proportional to Q squared, two slashed, and the second one is the proportional usually to the mass. So the kind of diagrams that participate here are the perturbative, quark condensate, two pair of quarks, and the gluons. And the mixed one is 0 in this case. So here we have the QCD sector. Pi 1, you have this S squared times a log. Then the gluon condensate is proportional to log. Then the 4 quarks are proportional to 1/S, and the other condensate. And pi2 the same. S times the log. The first term is proportional to the chiral condensate. This is in the chiral limit. The second one is the mixed gluon condensate, chiral condensate over S, and then the other term. So if we make the contour integrate with the kernel equal 1, just all this contribution vanishes. Yeah? And this is the pair of, we have these 2 equations. So we need, I didn't say it, but of course, in this case, there are 4 equations, but 6 parameters to determine it, so we need some inputs. So f pi and m pi. Here, by setting the nuclear mass, I think that's it. Yeah, with the gluon mass and with the background saturation approximation, this condensate is the chiral condensate to the square, and here we can split the gluon condensate times quark condensate. We can obtain the Hadron threshold and this coupling, nuclear coupling constant. So, yeah, sure. How do I get? It's one of the parameters I want to obtain. Of course. One of the inputs is the chiral condensate and the gluon condensate. Yeah, yes. So there are 2 equations, and basically we can get from other channels. Yeah, well, actually, I do not include the result of these channels. The chiral condensate and the gluon condensate are well known from other channels calculated with the more precise. Yeah. Yeah, no. In this case, only nucleons. Okay, the next resonance is the Roper resonance. I think it's higher than 1/2 of the square root of 1.26. So in this case, it's not needed to include this resonance. In the axial, actually, yes, it's important to include the A1 resonance, but we will not do it here. Okay. We can work with the expansion in terms of magnetic field, because it works in the same way we expand in this formalism the gluon condensate. So basically, it behaves like the same. This is the green function. This is the Schwinger phase in the Schwinger-Fock gauge, and we can expand it in terms of powers of B. So the propagator will include can be expanded. So it behaves the same as the gluons, and what we get are, at the end, are powers in terms of EB over SL. I have to say that a medium effect usually cuts this. There's not valid anymore this feature. I said that the phasors cut exactly the OP series, the operator product expansion series. For example, their finite temperatures, the appearance of extra the energy density of the gluon fields will break this fact. It's the terms logs over S squared. So in principle, you have to incorporate the infinite series of OP, but they are decreasing over the OP of dimension n over S0. So if F0 is big enough, this can be approximated to 0. And well, in this case, this will kind of happen with also with magnetic field. We will have an expansion, so in terms of S0. So this is small b, but it's not that small. So we can reach up to S0, basically. Okay. So in case of pions, for example, we can parameterize it with a pion velocity that is related with the decay constants. And also, we can define the screening mass as the pion mass divided by the pion velocity. And in case of fermions, we can put this expanded propagator. Here is notice that here there's an anomalous magnetic moment. Okay. So the external magnetic field that we will write in this way. So it's the magnetic field times this perpendicular antisymmetric tensor will produce a combination. We can see the structure of the form factors and also for the condensates, including this combination of G mu, epsilon mu, and all that. So chiral condensate will split in different new condensates. Also, gluon condensate will be split in perpendicular and linear. And this gamma tilde is this combination with this tensor. Well, one thing we found is that the Ward identity is still preserved with this Q, including the electromagnetic field. And we just want to pick, this is the general separation of the correlator. We just pick this one, this term only, and this another term, setting the perpendicular momentum going to 0, which is not the rest frame. So here are the results. First of all, the pion mass. We need inputs. So one of the inputs that is a chiral condensate. Because chiral condensate has been calculated in a lot of models and techniques. So we take from lattice for the Nambu-Jonas-Lassini models, and then we can get the pion mass in two ways. We can obtain it from Nambu-Jonas-Lassini, or this is a common consideration that the quark mass runs in the same way like the pion mass up to square. And also there's a third condition that the quark mass is constant. So here, for example, we see that the pion mass increases. This is the pion mass from Nambu-Jonas-Lassini, and this is the quark mass, okay? But as an input, the pion mass from Nambu-Jonas-Lassini, and this dashed line is with this condition. Also, the pion mass, okay, this is the result, the Nambu-Jonas-Lassini result, and the pion mass I can get with this constraint, the yellow one. If we set the up and down quark mass as constant, it decreases. So we can see that this is not possible. So for comparison, this is chiral perturbation theory. The pi and decay constant, the parallel pi and decay constant, we can obtain also from the modular Lassini, the pion mass. This is the orange one is the constraint of the quarks, quark mass with the pion mass, and we can see that give the same result. Quark mass constant and chiral perturbation theory give very different results. The hadronic threshold behaves the same like in this case. Okay, and this is the gluon condensate. It's basically constant. Those points are the lattice results. Okay, I have to run, so let me show. We just pick. This is the nuclear correlator. We split all the possible shapes of the correlator. We just pick 4. So the hadronic threshold, we have the different from the proton and the neutron. We have in general everything different. There's the couplings, you see, also different. There's the perpendicular velocity, decreases very well, and also the polarization of the chiral condensate. We have different results. This is the susceptibility. Usually, all the results known are use the same result. These have different, but all in the same range of the known results. And the masses, this is the mass parameter. So we have the proton mass parameter increases, the neutron decreases, and here this is the full nucleon masses, which include the anomalous magnetic moment. And just to finish, we can extract the axial coupling constant with this channel. Nucleon, axial, nucleon, this is proton, axial current, nucleon current. So this is, the form factor is parameterized with the axial part, pseudo-scalar part, unit and tensor part. So after Fourier transformation, we try to find the way to keep only the axial part. So just making the trace multiplied by the gamma matrix, we can avoid this. Well, there's a double phasor, double energy, sum energy, finite energy sum rule, and we get this result. So, and I'm finishing. We just put the results we obtained from the nucleon channel, and this is the axial, the behavior of the axial coupling. So it increases. We have no other works to compare with, so we expected that somebody else obtained this. So, just to finish the reasonable, I think there are reasonable results. B is confinant. Now that there's S in all the channels, S0 increases. So this is a sign of confinement. And well, we can do a lot of things here. Obrigado.
That biomass from NGL is an input, right?
It's an input.
And which one has that behavior that will increase with B? That's neutron pion mass, right?
No. All the pions I calculate here are charged. All the pions here are charged pions.
Oh, okay.
Chillán.
Hmm?
You take this from Chillán, the input.
Some input at the beginning, the requirements.
Thank you for the talk. So this is not my area, so I don't know if maybe the question is dumb, I don't know. So could you please explain a little bit more about the meaning of S, the threshold? Is that a quantity that I can access for another approach, like an experimental, so I have like an idea what it's supposed to be or something like that?
Yeah, sure. Well, let's see this. Yeah. Actually, this is the threshold that separates the sharp or identify the resonances for the overlapped resonances. So when you, for example, you have a finite temperature, all the resonances start to spread. So this means that the hadronic threshold will move, in this case, to the left. You see, because all the resonances start to overlap if the width starts to increase. And that's why it's considered as all the parameter for the confinement. So yes, you can access it when you see the spectrum, the spectral function, and you see that you can consider all the contributions, and then you cannot identify one of the other. You just keep the sharp ones. This is the meaning.
Why it does appear like a natural parameter expansion in the EB over S, something like that, QB over S? Why it does appear like?
I know this is because analytical, because we our integration path if of S0 on the hadronic threshold radius. So this is what we would separate. In general, the sum rules separates with this threshold what are the hadronic degrees of freedom from QCD. So it's
yeah. I just have another question, sorry. So by the end of the presentation, you introduced this decay constant F pi, but you call it like a parallel F pi. Like, what is the meaning of a parallel decay constant? Why is it an important parameter to study?
Well, this is the decay constant. You know, it's related with the decay of the pine, for example. So the axial current is proportional to the decay constant. When you have a magnetic field, it breaks the spatial symmetry. So you will have the perpendicular part of this axial symmetry will behave differently. So this is parameterized with the hadronic threshold. With the decay constant.
Two small questions, Christian. Can you explain again how do you get an estimate for the condensates in terms of B?
The condensates, okay.
They become B dependent, but how do you estimate their value?
Okay, but well, first of all, the chiral condensate is an input.
Yeah, but F square and so on, how do you do that?
G square.
Or G square, sorry.
Yeah, because we have this tower of equations, and this is one of the
and they are self-consistent?
Yeah.
Because I guess you have more equations than variables.
For example, I didn't put on the equation of finite magnetic field, but here you have, for example. So you have 4 equations.
But there's no B here yet.
No B, but.
But you solve the set of equations.
I solve. I have to say that there are more equations when you have a medium effect. You get more equations, but also you have more condensates. So, well, you can say that some condensates you can
so you lose a bit of predictability.
Avoid them, and then just get the mean.
Is there a restriction on how large B can be?
Yes, it's the hadronic threshold. But the hadronic threshold.
But that shifts with B.
Huh?
Because in principle, let's say the more recent data of Delia and colleagues show that at very large B, confinement should be lost. So can you see that in your approach?
No, indeed, the hadronic threshold in all the cases increases here with B.
But at some point it should go down again.
Hmm?
It should go down again at B, increases very large.
Yeah, but we didn't reach this sector. Because also you have to consider.
Yeah, but
this is
their
zero
predictions is at zero temperature as well, I think. Or not. I think they say something like that.
Yeah, at finite
Confine
temperature.
at B very, very large.
At finite temperature, you can expect that. At finite temperature, you can expect that, but at zero temperature, no. Yeah, but you see, we reached about 1 GeV squared, so it's far from the.
Super simple question. You're trying to push magnetic field basically to hadronic scale, maybe over 1 GeV squared or something. But it seems like when you have magnetic field even just larger than the quark masses, you will have a lot of new poles coming from the Landau levels, and basically you have to treat them like those delta function peaks, I think, not like a continuum. Isn't that right?
Well, actually, we're not working with Landau levels, so it's all summed up.
But shouldn't you? That's exactly the question. Since you are trying to push magnetic field to basically hadronic scale, means that you must have many quark delta peaks corresponding to each and every Landau level up to that energy of S0.
Well, actually, we did with the Landau levels all the we don't use it here because we have loops with up and down different. So this is a problem with Landau propagators because the charge is different. So they are not. We lose this property of
Translation variance is lost.
Yeah, yeah. So, if you have the same quarks, we get something like that. So these poles are included and give similar results. But for example, just point like a curve. In this case, the strike curve. In the other case, like scaled, but much in the same way.
Just a comment. I mean, it doesn't matter if you use Landau level prescription or another prescription; it should show up anyway, right? I mean, in the zeta function or whatever this pose he's talking about.
Yeah, actually, we found out that it's.
Doesn't matter which prescription.
Yeah.
Hi, thank you for the talk. Can you come back to slide number 7, please?
Yeah.
When you say the hadronic threshold acts as another parameter, can you please explain to me it is related to which phenomena, physically speaking?
The confinement. It's related with the confinement. As I explained recently, it's because when you have finite temperature, on the resonance tend to the width of the resonance tends to increase. So the overlap, imagine those resonances. So the overlap will start before, So if S0 denotes when the resonance start to overlap, finite temperature will move this threshold to the left. Up to then if you have a very high temperature, all this resonance will melt, basically. So your S0 will be here, near to 0, but well, not near 0. Actually, yeah, not 0, but approaches to 0. You have S0 for each channel, yeah. It's different for every channel.
Okay, so I think you have to go to the next. Let's thank Cristian again.
Okay.
The next speaker, Manuel.